Okay, we have a water in a tub problem. Got this tubby tub. Gonna really take this bath or something, man. Gonna heat up this water. They give us the temperature of the water heating up in the first 20 minutes in this chart. And then the next few minutes is gonna be something different later on. But when you see strictly increasing twice differential function, twice differential, that just means your first derivative exists, your second derivative exists, everything's smooth and curvy. You ain't got nothing to worry about there. So that's just friendly stuff when you see that stuff. You don't even worry about it. But then part A is just talking about W prime. You know that's your derivative, and we know derivative is slope, right? And so it says to approximate the slope at 12. So 12 is in between the 9 and the 15. And so I chose this point here and this point here, jotted those down, and just did my slope formula. Subtract the y's on the top, x's on the bottom. You have the calculators, round the 3 numbers after the decimal. That's going to be degrees Fahrenheit over minute there. And then please read the problem, okay? It's one thing to find it, but then it says show the computations that lead to your answer, which I did. And then it says using the correct units, interpret the meaning of your answer. You know what a derivative is. This means at T equals 12, the temperature of the water is increasing at approximately 1.017 degrees Fahrenheit per minute. So since it's positive, the temperature is increasing. If it's negative, the temperature would have been decreasing right there. So you know what a derivative is. That's how fast that stuff is changing right there. So part A, we're good. Part B, I kind of like part B. It just said to evaluate the integral of the derivative, right? And you know, when you integrate the derivative, you're going to get the original function right there. So when I integrate the W prime, that's going to give me my WT, and then you have a definite integral. So evaluate that ever since, like we've been doing all year. Like use your fundamental thermocalculus, plug in the top number minus plug in the bottom number, and then they give us these numbers from the chart there. W of 20 is our 71, W of 0 is our 55, and you're just subtracting the ending temp minus the beginning temp right there to get the 16-degree difference. And that's what the integral is going to do there. It's going to give us the net change in that temperature of the water from the 0 minutes to the 20 minutes. So again, it does say interpret the meaning of this. So you have to make sure that you're not just stopping too soon at the 16. Write that stuff down. You don't need a whole big paragraph right there, just short, sweet, to the point. What does that stuff represent right there? And you know, when you integrate the degrees, you know, this is, you know, you integrate the W prime, which is going to be like degrees per minute. That's going to give you just the degrees right there. Just for your, you know, that's going to give you W. W is already in degrees right there. So that helps you to interpret it sometimes. Okay. Letter C talked about the average temperature, and they use the average value formula, that 1 over B minus A times the integral from A to B formula. That is your average temperature in the water, of the water. And it says use a Left Riemann Sum. Now, I believe it was the 2007 video, I explained how to do the Riemann sum left and right without the use of a picture or anything like that. And that's what we're going to do here. So we have this integral, and they're going to say either use a Riemann sum or a trapezoidal sum. It seems like it's like that every single year. So you got to carry over the 1 over 20. When you approximate this integral, Riemann sum means you're using rectangles. You could draw the rectangles if you want, but here's how you do the Left Riemann sum. I'm going to show you how you get those numbers again. It's just a pattern here. I think you'll like this. Left Riemann sum, you start at the left. You're going to start at the 55. You're going to go 55 times the distance between the 0 and the 4 times 4. And then you go plus 57.1 times 5 plus 61.8 times 6 plus 67.9 times 5. And that's the exact numbers that I got down here. Now, this is a calculator problem, so you can just plug all this stuff in there. Be careful with that. When you do an average value problem like that and use that average value formula, the units always stay the same as whatever it is that you're integrating, okay? Because you're just averaging out. Like if you average out your test score, it's your percent. It's not like percent per minute all of a sudden. It's just your percent. So when you average out the temperatures, it's just your temperatures right there. That's on average. That's how hot that water was, 60.79 degrees Fahrenheit. I do round to 3 numbers, except that was exactly 60.79. There was no third number to round that to. Just for fun, let's do a right Riemann sum if it asks for that. Right Riemann sum, I would go 71 times 5 plus 67.9 times 6 plus 61.8 times 5 plus 57.1 times 4. Midpoint Riemann sum, we haven't seen that yet, but we will, and we'll show you how to do that when the time comes. And trapezoidal sum, you got to draw on a few trapezoids and know that area formula for a trapezoid. Now, That's the first part of that one. Also, what it asks for here is this answer an under or over estimate? Okay, and what they want to hear, they don't want to hear under or over because the rectangles are above or below the actual curve. That's how you know, but you got to actually kind of think about that, right? So notice what I did. I didn't do this with that picture, so I don't even have any rectangles in front of me, but what I'm looking at is these values are increasing. So you could take any increasing function. Remember, the concavity doesn't matter. Just draw a normal increasing function. And if I do a left Riemann sum, I'll start at the left side of the interval, go up to the curve, draw the height over, go up to the curve, draw the height over, and I know if those rectangles are below the curve, that's how I know that thing is going to be an underestimate. But you can't say because the rectangles are below the curve. You got to tell me what that thing is doing, and it's going to be increasing right there. So that you got to say that's an underestimate since the W of t is increasing. Also want to mention sometimes those values go negative, and then you would just include those negatives in there. Unless there's like absolute value bars in your problem, then you would just make them all positive right there. Just kind of use those values. Okay, and then the last part, letter D, it gives us a different function. So that chart is only for the first 20 minutes, and then in between 20 and 25 minutes, our water temperature is going to have a derivative of this. All right, and then it says, what is the temperature of the water at time t equals 25? So when you, this is how fast that temperature is changing. So I'm gonna need to integrate that to get the W back to give me the temperature. But here's the deal, like when you integrate the W prime in between 20 and 25, Math 9, that thing, this is a graphing calculator problem, it gets you this, right? Now use common sense too. You know your water temperature didn't go all of a sudden from 71 degrees and in 5 minutes went by, all of a sudden it's 2 degrees. That doesn't make any sense. This is just the net change in between 20 and 25 minutes. That's how much that temperature changed. That's how much it went up, okay? Now, you already know though at 20 minutes, our temperature was 71. So that's like the initial position type of problems there. You gotta take into account what it was at the beginning at 20, and you could have even set that up like that at the beginning if you wanted to. If you wanted to know what that temperature was, you could have said, okay, this is going to be 71 plus the integral between 20 and 25. A lot of times I'll set that up right away at the beginning and I won't forget about it, you know, but that just gives you the temperature change added to the 71 you already got, and then you got that 73.043 degrees Fahrenheit. Oranges.